introducing me, my name is Arnaiz del Pozo. I work at Universidad Politécnica de Madrid, and I'm going to present on behalf of Charlotte, who lives here in SINTEF, and also on behalf of my professor Ángel Jiménez Álvaro, who is a thermodynamics professor. I'm going to discuss about advanced methanol and ammonia plants utilizing a novel concept for hydrogen production, which is gas-switching reforming. And my research is carried out in the framework of a postdoc position of a Margarita Salas grant with European funding, and I'm working right now as a visiting researcher at SINTEF. The way we structure our work, which consists of techno-economic assessment of chemical and energy plants with a sustainable focus, is in the following way. At first, we carry out ad hoc models of unit operations, which require special attention with regards to a spatial dimension, temporal dimension, and for that we use an equation-oriented solver, right? And the outputs of these models are connected to a stationary plant model, which is developed in Honeywell Imaging Design, right? This allows us to carry out a preliminary mass and energy balance and equipment sizing, and that information is then transferred to an economic assessment tool that we have developed in Excel using Visual Basic. This enables to calculate things like levelized cost of product, internal rate of return, and so on. On an upper level, once we have developed a collection of process model of chemical plants or energy plants and carried out the economic assessment of those plants, the outputs, both from an economic perspective, from an energy perspective, and also from an environmental perspective, are transferred to a system scale model in GAMS. And this basically allows, subject to certain environmental and location constraints, to optimize the technology mix to minimize the system scale cost. And these are very interesting outputs for potential policymakers. Right, so everything from the very basic modeling, core modeling, to the high-level perspective. This is the scope of my research. I focus primarily on these three levels. Okay, so the presentation for today is basically going to consist of our experience on how we have connected level 4, a dedicated model, to the stationary plant, right, using CAPE-OPEN. Specifically, the gas switching reforming concept connected to the different synthesis loops for methanol and ammonia. So first, let me give a very brief understanding of what this gas switching consists of. As you may know, for ammonia and methanol, there is a preliminary step of generating a single stream. This is typically carried out with steam methane reforming units. This is an advanced concept, right, which consists of fluidized beds, which are alternatively exposed to different feeds, right, and have a transient nature operation. There is within the reactor volume an oxygen carrier that carries out the reforming of the natural gas, which is later oxidized with an airstream, and then with a fuel stream it is transformed back to the metal to behave as a catalyst in the subsequent step. So note that this is modeled as a lumped system, as a continuous stirred tank reactor, the most simplistic approach. And once that assumption is taken, we can carry out the mass component and energy balances to the system. Okay? With a further simpler assumption of considering the gases ideal given the high temperatures and low pressures, we can decouple the balances. Right? So note that in this reactor a cycle is taking place. The solving of these equations leads to this kind of reactor profile. Okay? If you notice, we have first a very steep decline on temperature, where the reforming is taking place. As you may be aware, it's an endothermic reaction. And we have, please consider that these are outlet compositions. We have the syngas being generated, right? Hydrogen and carbon monoxide. We have the oxidation step, right, where oxygen is being entirely consumed, so there's only nitrogen in the outlet, and then we have a reforming step where the oxygen carrier is reduced, right? And here a fuel step provides the heat for the endothermic reaction. Right? So this would be just one reactor. Now we have a cluster of reactors, right? And we make a time average at each point. Right? If we have the first reactor at time 0, second reactor displaced a certain amount of time, we have this kind of scheme, right? And we time average the outlet streams of the reactors working in reforming, the same for the reactors working in oxidation, and the same for reduction, and we obtain a quasi-stationary output for the stationary plant. Yeah? And this is the evolution of the gas switching cluster. Okay, so let's go on to describe a little bit how this gas switching reactor cluster is integrated in the methanol synthesis concept. For methanol, we have these reactions taking place in the synthesis loop, the proper methanol synthesis and the reverse water gas shift. And we must introduce a syngas stream with the following module, right, because of the stoichiometric requirements. So we have our natural gas inlet, which is mixed with steam and CO2. CO2 allows us to reach this module, because otherwise the steam reforming produces 3 hydrogens per molecule of CO. And then we have our feed to the synthesis. The synthesis loop requires a purge to avoid accumulation of inerts, and that purge precisely is then fed as fuel to the reduction step. Once the fuel is combusted, we have reduction gases, cool down, remove the water, we purify the CO2, right, which is then routed back to the natural gas stream, and of course there is a small bend. But this system allows a very high carbon efficiency, minimizing the emissions relative to conventional methanol processes with autothermal reforming. We need a purification because there is some mixing between the outlet feeds, if you regard the temperature profiles, sorry, the reactor profiles. And finally, with regards to the airstream, we just have a power block integrated. Okay, so this is the first concept. This is how we integrate the gas switching reactor cluster in the methanol concept. For ammonia, it is slightly different. In this case, we just need to assemble 3 molecules of hydrogen and 1 of nitrogen. And to do this, we just have steam and natural gas. We want to maximize the hydrogen yield, right? And subsequently, we have a water gas shift unit. This further converts the remaining carbon monoxide, right? And also, because this reaction is exothermic, generates steam that we can deliver to the natural gas inlet stream. Then we have a separation where the pure hydrogen is obtained in a pressure swing adsorption unit, right? And we have an off-gas fuel, which is very conveniently used as the reduction inlet, right? This contains mostly carbon dioxide and some unconverted species, and some hydrogen that is not recovered because the recovery is not 100%. And again, we have a purification unit. Bear in mind that there is some mixing of nitrogen here. And this concept allows inherent carbon capture and storage for an ammonia concept. And finally, we need our nitrogen stream. Again, we have an air stream to oxidize the oxygen carrier. And the nitrogen is easy, at pressurized conditions, it's easily purified to provide the stoichiometric amount of nitrogen for the synthesis. Right? So these are a novel advanced concept for chemical commodities production, in the understanding that they may become potential energy vectors of the future. But what I want to highlight in this presentation, that the connectivity between CAPE-OPEN with CAPE-OPEN between the Scilab models and Unisim has been extremely easy and extremely simple. I've just required these 3 commands, right? And just inlet ports, the air, fuel, and natural gas streams, and the output. at which, and these are the time averaged outputs of each reactor step for the whole cluster. And of course, also as an input from the stationary model, it is convenient to set up the number of reactors externally and obtain fluidization velocities to check that more or less our assumptions regarding the modeling of the reactors are reasonably within the range. So again, just highlight again the simplicity with which we've been able to carry out this complex simulation. It might look very easy on these block flow diagrams, but yeah, in order to fulfill and to comply with the energy balances of the gas switching reforming, it has taken quite some iterations, which would have been extremely tedious had it not been for the fact that the model output is immediately transferred to a process stream in the simulator. Well, just to give a flavor of where is this leading, just some economic results with the economic Excel tool that I was mentioning. Yeah, levelized cost of product of the advanced methanol concept is around 240-ish, which, for you to have an idea, constitutes a 6.5% levelized cost reduction relative to the typical autothermal reforming methanol plant. Right? And with regards to ammonia, we obtained a levelized cost of 330, which represents approximately 14% cost reduction relative to conventional SMR, ATR, and synthesis. Yeah, so all in all, results pretty interesting from an economic point of view as well. To summarize the presentation, again, let me emphasize the simplicity and how fast it has been to make these simulations between Unison and Scilab thanks to CAPE-OPEN integration. In particular, for this presentation, a transient gas switching reformer reactor is connected to a stationary plant. We've also been working with electrolyzer models or with membrane reactors, which are much more troublesome to represent in this simulator. Right? And also a very convenient feature that the specifications of the Scilab model can be provided from the process closure. And this has led up to now to 7 published research items and 2 more on the way. I think that the 2 publications regarding methanol production and ammonia production with these gas switching reforming concept are perhaps the most representative of what we have accomplished during this collaboration between SINTEF and Polytech. Okay, and with this, I conclude my presentation.